Good morning. I hope everyone can hear me. My name is Vincent Torres. I'm the Associate Director of the Center for Energy and Environmental Resources. My presentation this morning is on driving natural gas systems to reduce greenhouse gas emissions. And basically, it is a project being conducted by the University of Texas at Austin to reduce greenhouse gas emissions in the natural gas systems used in the upstream oil and gas industry. It's a project being led by Professor David Allen, the Associate Director of the Center for Energy and Environmental Resources, and Dr. Paul Navratil, the Director of Visualization at the Texas Advanced Computing Center. Professor Allen was going to give this presentation this morning, but unfortunately a personal matter came up that he had to attend to at the last minute, and he's asked me to substitute for him. Next slide, please. Methane, the main constituent of natural gas, is a potent greenhouse gas. I think a lot of folks know that. What may not be as widely known is that on a mass basis, methane in the atmosphere produces up to 120 times as much warming as CO2. Next slide, please. Since 2013, there have been extensive measurements of methane emissions from the oil and gas operations made using multiple techniques. Primarily, this research has been done in the United States. Some of the methods that have been used are discrete direct measurements of sources, a person using an instrument going out to the field and measuring what's coming off at a particular location at a particular point in time. Another approach is using fixed ground-based measurement systems where a number of sensors are placed at a location. They may operate continuously or they may operate when triggered to do so, but they would be at one location and they would be fixed and not mobile. Then you have mobile ground monitoring where literally you have vehicles that drive around on public roadways and make measurements of the emissions in the air where they're able to sample and do so downwind of the sources. So this gets to be quite tricky, and of course, it's only a snapshot during the time period that they're making their measurements. Another snapshot approach is doing that from the air in aircraft, where you might have an aircraft that flies what are referred to as transects, which is basically moving up and down, forward and backward in a particular prescribed pattern, trying to crisscross the area that they're making the measurements in. Once again, this is great, but it's only for the day or period of time that the measurements were made. Then you have satellite measurements, and satellites are from space with specialized instrumentation that will make measurements during the pass when the satellite is overhead. I'm wanting to make sure that everybody can hear me. Kayla, can you hear me? Hello? Okay. And then the different approaches that I've just described provide complementary information to each other. So when you're trying to understand all of the emissions, because some are discrete, some are snapshots in time, some are only for a short period of time, you really have to piece all those together to get a picture of the emissions, because they're not emissions that may occur continuously in the same direction with the wind blowing and at the same concentration or level. Next slide. So what do we find out from these from this research that's been conducted so far? On a global basis, the emissions have been estimated as approximately 2% of the methane that's produced. The result is that this erodes about 2/3 of the climate advantage that natural gas has relative to coal based on its lower carbon dioxide emissions. A second major finding is that a small subset of these sites and devices account for most of the emissions, As an example, in the Bartlett Shale, which is near the Fort Worth area of Texas, 2% of the sites in the Bartlett Shale led to 50% of the emissions. 19% of pneumatic controllers are those devices that are used to operate valves and control equipment at well sites, lead to 95% of the emissions. And the big challenge, of course, is that these emissions are intermittent. They're not consistent in level. They happen at times when you may not expect them. Some are associated with operations, so they may happen periodically, and they will most likely reoccur. And then measuring these emissions has been very expensive because up to now you've had equipment that has been in its early stages of development, and it requires people to go out and or people to go out and operate equipment if there are discrete measurements that are being made. So you, at the end of the day, have some limited information in making these measurements, and it has been very costly. Next slide, please. This was a video that I had hoped to be able to show illustrating in the Bartlett Shale exactly how the emissions vary over time and location and intensity. It's almost like a board with different spikes appearing at different locations randomly and without any sort of pattern. And so it makes the ability to find emissions extremely challenging and expensive. Next slide, please. So given these challenges, based on the technology, what are some approaches that might be successful? What we would like to try, and what I'll be talking to you a little bit about in just a few minutes, is that to do so, you really need to take a strategic approach targeting the high emitting sources, because this will probably lead to the most effective, economically efficient reduction of emissions. But then once you know where those emissions are, you then also need to couple that with finding and fixing those emissions. And so understanding the level of an emission or where it has occurred is one thing, but understanding how you can then go out and deploy field teams to fix the leak is the holy grail. You want to be able to do that as quickly as you can, and you want to be able to do that before any leaks get to be larger, or if they're repetitive, to try and fix the problem if there's any way to do so, particularly for your larger leaks. Next slide, please. So I'd like to talk to you a little bit about Project ASTRA, which is a project that we are involved in. It is a major research project being conducted by the University of Texas, led by the two individuals that I mentioned at the beginning, Dr. Allen and Dr. Navratil. And this is a project that we hope will demonstrate a novel approach to measuring methane emissions from oil and gas production sites using some of the latest sensing technologies and data analytics that we are now able to do with some of the high performance computing methods that are available. If our project is successful, it will transform methane emission detection from these labor-intensive surveys, efficient that are inefficient at finding and slow to repair emissions, to sensor-intensive, continuously monitored sensors that will be efficient to deploy and at a lower cost. You can look at the graphic on the right of this slide. All the little light-colored areas are well pads, and those well pads may have multiple wells on them and multiple pieces of equipment. So what you're looking at is trying to identify leaks from literally thousands of highly dispersed sources. And by the approach of Project ASTRA will be to set up a network of sensors strategically placed amongst those sources so that you can then try to determine where the emission is coming from based on wind direction and some of the other data analytic approaches that would be used. Doing so by being able to continuously monitor these emissions, we can then quickly find, identify, and repair what the emission might be. Next slide, please. So Project ASTRA is divided into three major activities. The first one, what we call the West Texas Methane Intercomparison, is it's taking and trying to understand the latest sensing technologies that are currently on the market, that are field ready, meaning that they can actually be deployed to the field, and then to take those instruments and understand a little bit about their performance, how accurate they are, their robustness, and what their costs might be. A second major component is the digital methane challenge. So now you have sensors, you've tried to identify what those sensors might be, but where do you locate them? How many do you put out there? What type of instrument do you need to have? So the digital methane challenge is an activity that was developed to basically design a digital twin of the pilot area where we were going to deploy this project, and to determine the optimized design of the sensor mesh. In other words, where do you space them? Where do you locate them? How far do you space them? How many do you place? And which types of sensors would you put in a particular location? So now you have the sensor design that you've done digitally. You have the instruments that you've identified that are the best available instruments at the moment in time. And then the holy grail is putting those two together and conducting it literally a field exercise where the well sites are using the sensors that you've identified. And at this point in time, I'd like to recognize the partners that we have had participating with us on this project. A project of this scale can't happen unless you have the cooperation and the participation of partners like this. And we've been very fortunate to have Chevron, the Environmental Defense Fund, ExxonMobil, the Gas Technology Institute, Microsoft, Pioneer Natural Resources, Schlumberger, and of course, the University of Texas to help us make this project possible. So I want to thank all of those folks for helping to make Project ASTRA a reality. Next slide, please. So what do we learn from the sensor field intercomparison? Well, there are basically three questions we wanted to answer. What precision and accuracy can be provided by low-cost methane sensors? What is the data capture rate? Meaning, if you had 100 measurements that you needed to make, how many of those measurements were successfully made? And does the performance of the instrument change over time? In other words, how robust is the instrument? We basically set up a site that you see here with the 7 instruments. The important thing to recognize about these instruments is they have to be completely self-contained. They provide their power using solar collectors. A battery provides reserve power, and then the sensor operates completely off of that power and has its own cellular communication system to report data. And they operate continuously, unmanned or unstaffed during the entire time period. They also have to be able to withstand the particular climate that they're subjected to. And this project was done in Midland. And if you've ever been to Midland, you know how windy and dusty it can be in that area. Next slide, please. So the test, the field intercomparison was a field test that took place over a 9-month period from October 2020 to June 2021. There were 7 sensors that were compared. And what we did is as I mentioned before, these sensors operate continuously without any sort of supervision or intervention by the manufacturers. In addition to having continuous measurements, we then subjected each of these sensors to 4 concentrations of methane that were certified to a particular concentration. at different times during the 9 months, typically 2 to 4 weeks apart. They did not know when these, what we call challenge tests, were to take place, and they didn't know what concentrations we were using. It was our way to check to see how the systems were performing over time and how these measurements changed over the 9-month period. We compared those using a very high quality methane analyzer that was also operating continuously, collecting samples at the same locations that they were, or within about 6 feet of where they were located. And it had a 1 ppb, 1 part per billion precision, at a frequency of 1 hertz. Next slide, please. So what do we find out? Well, multiple sensors had a 10 ppb hertz. These are what we called our high resolution sensors. Very low sensitivity and very quick response. Some of the other sensors sort of fell into a second category. We call them our moderate resolution sensors. They were not quite as sensitive. They were able to make measurements at concentrations of 500 ppb and changes in concentration at 1 minute resolution. Their data capture rate was pretty high and typically above 95%. And their performance was, most of them were affected by the dust, but overall their performances were pretty good, except for interference with the dust. The final report on this project is on our webpage, which I will have at the end of the presentation. Next slide, please. So where are we? At this point in time, as I say, the methane sensor intercomparison project has been completed, that component. The design stage of the digital methane challenge is also completed, and we have launched the pilot phase, the phase 3. I was just out in Midland last week, overseeing and coordinating the installation of the first phase of the sensors that are going in based on the sensor network design that we came up with. And we'll be installing some additional sensors when the remainder sensors that are part of the network are delivered. So we are well into phase 3 of this multi-phase project. Next slide, please. As far as the network design, there are a number of questions that we're trying to understand. You know, you can deploy very expensive equipment that has very high sensitivity, but you can probably only afford a few of those sensors. You can deploy less expensive sensors and have more of them, but then you lose some of the accuracy of measurements and their ability to capture all the events that may occur. So your network design, you're trying to optimize how many of each of those types of sensors do you need to have, where do you need to have them, and what sort of time resolution do each of these sensors need to have. Also, what accuracy do you need to have based on how far away they are from a particular source? The closer they are, the higher the concentration will be. The farther they are, the lower the concentration. So the need for a higher resolution instrument. So these are the questions we hope to find during this study once we have completed and have started the actual measurements at the sites. Next slide, please. As far as data analytics, so now you have all this data coming in from literally 60 different sensors, and you have clearly emissions that are coming in, emission measurements that are coming in. And so you want to understand how those emission measurements can help you determine where the sources of the emissions are and how quickly you can get folks out to that location to repair them. So our data analytics are helping us do that. And we are looking at different approaches to data analytics. Of course, some of them that we had already developed and others that we hope to maybe learn could be possible, using other approaches to do this. One possibility of gathering some of those ideas might be through a hackathon to focus on improved data analytics once we know exactly what the data are we're getting and can share it with others. Next slide, please. So basically, this project, as I mentioned, is well underway. I want to once again thank our partners that are listed here on this slide. It is a very exciting project given all that is occurring at the moment with different changes in regulations taking place. And we look forward to the results and a successful completion of the project. Thank you.